Totally.
Hello, and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. I'm David Sankel, a principal scientist at Adobe and an active member of the C++ Standardization Committee. My experience spans microservice architectures, CAD/CAM, computer graphics, visual programming languages, web applications, computer vision, and cryptography. You can find my full bio in the resources section on your screen. For those of you who may be unfamiliar with ACM or what it has to offer, here is more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. You can see some of the highlights on your screen. ACM provides access to the ACM Digital Library, the world's most comprehensive database of computing literature, leading publications and global conferences that draw top experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards, and the ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. Before we get started, we'd like to quickly mention a few housekeeping items shown on the slide in front of you. If you have questions at any time, please type them in using Zoom's Q&A button. We'll organize the questions as Titus speaks and try to get to as many as possible. This session is being recorded and will be archived. You'll receive an email notification when it becomes available, and check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a minute to fill it out to help us improve our tech talks. Today's presentation is Design is Testability with Titus Winters. Titus is a senior principal scientist at Adobe, focusing on developer experience. He has served on the C++ Standards Committee, chairing the working group for the design and evolution of the C++ Standard Library, and he's had a huge impact there. He has also served on the ACM IEEE AAAI CS 2023 Steering Committee, helping set curriculum requirements for computer science undergraduate degrees, focusing on the requirements for software engineering. Titus was a thought leader at Google for many years, focusing on C++, software engineering practice, technical debt, and culture. He is also the lead author for the book Software Engineering at Google. Titus, without further ado, take it away.
Thanks so much, Dave. And thank you, everyone, for having me. So let me see my slides. We're all good? We're good. All right. So first off, a minor preamble note. I still don't love the title of this talk. All of the short titles that I've been able to come up with feel kind of reductive or it may be inaccurate, and I'm not entirely happy with them, but anything that's large enough to capture all of it is just kind of too much of a mouthful. So if the title feels a little bit too clickbaity or inflammatory, especially if you come out of a design community, please drop me a line with a better suggestion or bring it up in Q&A. But as we'll see for the next 30 or 40 minutes, there is a lot more overlap in these two topics than I think a lot of us might normally be thinking. So there's a famous quote from Donald Knuth: "Beware of bugs in the above code. I have only proved it correct, not tried it." And this quote is usually good for a chuckle, but over time I've found that that chuckle might be more nervous than amused. As much as it was kind of a throwaway line for Knuth, I assume, it does actually speak to one of the essential important dichotomies in tech. That is, when we aim to develop something new or change an existing system, do we, think real hard, seek the proper design, and find a mathematical or logical or combinatorial proof that our code or change is correct? Or do we throw together some code and try it out and just see if it works? This style argues that exploration, experimentation, and hands-on experience tell us whether our software is actually doing what we want. And there is, of course, sometimes a third option, which is mentioned here for completeness. Just throw it at the wall and see what sticks. Move fast and break things, as Mark Zuckerberg famously once said. And this doesn't work, and even Facebook infrastructure has walked that back substantially. In the end, we need to mostly not be breaking things except for in extremely weird environments. As to this theory versus practice dichotomy, I see echoes of this in so many aspects of technology today. Thinking and proving and understanding is tied to a more academic strategy, to theory of computing, to software design, to out of fashion but still valuable notions of software architecture. While the experimentation and evidence approach is far more reminiscent of the more robust parts of industry practice: prototyping, experimentation, automated testing. And there's clearly a spectrum here. Very few real-world problems are handled only by thinking, but also very few useful systems exist where we only understand it through experience and experimentation, but have no theory behind how it works. Different companies, different teams, and even individual people are going to have preferences and biases along this spectrum, but there are a lot of ways to be effective regardless of where you fall on that spectrum. For example, I spent 2 or 3 of my 13-year stint at Google working with a guy, George Fairbanks, who spent his career in software design and architecture. He's been the editor of IEEE software columns on that topic. He published a lovely book, Just Enough Software Architecture, and he's worked with a lot of excellent software engineering and design scholars, people like Mary Shaw or Michael Jackson. We both have an instinct, George and I, that there are some fundamental lessons in software engineering that are missing for most engineers, even like mid-career engineers. And so going into this collaboration and coming from the testing suffices side of things, I was initially a little skeptical of George's idea that you could teach design or architecture in a useful fashion. How do you teach taste? But instead, over those years, what we found is the dichotomy is a lot less us versus them and more two sides of the same coin. I started to think about this the same way that I think about introductory calculus and physics and how they complement each other. Calc seems a little abstract and irrelevant on its own, but physics without calculus seems kind of unintuitive and arbitrary. It's a list of disconnected laws or equations where you have to memorize a bunch of special cases. Why is there a 1/2 here, you know? But if you put these two topics together, physics and calculus, the ideas and explanatory power of calculus combine brilliantly with our tangible, relatable, real-world experience of mechanics in a way that explains the practical and exemplifies or embodies the theoretical. And I think exactly the same relationship exists with design and testing. Here's my favorite example. Imagine we have an API, a piece of software that we want to test. I'm not going to specify what it is exactly. It could be a function, a class, a microservice, maybe even a whole program. What is enough testing for that piece of software? Until working with George, the best answer I had was, I'll know it when I see it, but there have been at least a few guideposts for, is this enough testing over the years? Many people, especially the security conscious, will tell you that if you are handling untrusted inputs, you need to use a fuzzer, and I will cover that soon. And any of us with any formal math or logic background might see people putting together a couple unit tests and calling that proof, but we also know that proof by example isn't actually proof. We could probably go on, but I think even just these two endpoints to think about, very heavyweight machinery like fuzzing for complicated systems, and a theoretical reminder that a single answer might not cut it, these two endpoints might be sufficient for now. So I'm going to go back to design, and I want to pause and reach into George's software design terminology. So let's talk for a moment about control. This is a tangent, but it's an incredibly useful one, I promise. Imagine you're working with a software system and you need to make a change. George argues, and I absolutely agree, there are roughly 3 scenarios you can be in with respect to that system and your ability to make change safely. In the worst case, you have no control at all. Making any change to the system comes with great fear. You don't know what is actually going to happen, nor do you have any good way to find out, short of trying it out live, with all of the commensurate risks that come from that. If you're in this scenario, you have a lot of work ahead of you. There is no room for fear in good engineering. Like SRE would say, no haunted graveyards. If you have systems that nobody is willing to touch because they are afraid of what is going to happen, it is imperative that you go in there and clean up that mess. You got to bust those ghosts. Over time, all software has to change. And if you cannot find a way to do that safely, you are making an awfully risky bet that the scary stuff dies off on its own before you are forced to change it. And if that forced change comes during an outage or security incident, you're going to have a very bad time. In the slightly better case, you might have statistical control. There are test environments, experiments that you can run to figure out, maybe not with absolute certainty, but good evidence that your change is safe. You may wind up spending some time and likely a significant amount of compute resource to build up statistical evidence of safety and correctness. But in the end, you can be pretty calm about the next rollout or release. This is where I see the majority of successful large software systems tend to sit. Through a combination of manual and hopefully automated testing, we build up enough statistical evidence to convince ourselves that what we are doing is safe, even if we don't necessarily understand the full ramifications. And we certainly won't be able to prove that. This is a little bit unsatisfying for a lot of people, but it is an important theme. Beyond a certain point, additional levels of proof or certainty or redundancy tend to be substantially more expensive and without commensurate improvements to the utility of our systems. Turns out that being 99-point-something% sure is often hugely cheaper than being 100% sure, and the utility gap between those positions is often invisible to most people. In the rare, probably best case, we might have intellectual control, IC. This is the state where you and hopefully your team fundamentally understand what the software is doing, how it works, what depends on what, and you can reason through the ramifications of a proposed change. This is wonderful, but is very hard to scale. As an example, if you need to make broad changes across many parts of a code base or a product, say upgrading language versions, if you don't have any sort of statistical control, you're left manually tracking down who understands each bit of the code in order to rely on their intellectual control. SC and IC are slightly orthogonal, and both are very valuable in different scenarios. With this vocabulary in mind, let's go back to our sort of quick and easy testing guideposts. Here's a very easy function, and it's in Python here so that we don't have to worry about sharp corners. Note, it's important here, there is no integer overflow in Python. If this arithmetic fails because of overflow, Python automatically upgrades the type in question to be arbitrary precision integers. Really, like, there's nothing hiding behind the curtain. This code is as correct as I can make it. Now, we already said, and we do know, proof by example isn't proof. But at the same time, with only a couple very simple tests, I can get a pretty substantial amount of evidence that my implementation of add1 is working correctly. In fact, I would give this set of tests at least a B-. I have to think a little bit to convince myself that the chosen input in the success case is robust enough to answer my skepticism. And there might be a couple of other success cases that would make me feel better about this, like adding 1 to 9999999. But the broader point is, proof by a couple of examples is actually pretty sufficient in some cases. It isn't proof, but it does give us plenty of experimental understanding, statistical control. So is the lesson that I want to draw here that one good example and one error case is sufficient testing? Let's see how we feel about that when we change from adding 1 to, say, decoding a JPEG. Anyone feel good about this code instead? What's the difference between adding 1 and decoding a JPEG? I would argue that it's control. We can look at add1, or more precisely the specification of that function, and we all have pretty good intellectual control on it. I'm hand waving over one aspect of this. If the exception handling in the add1 case is bothering you, don't worry, I will get to that soon enough. But by comparison, I would argue that no human has intellectual control over a JPEG decoder. We can certainly specify what it does, but that is not remotely the same as really being able to reason about it. So let's look at this another way and go back to this idea of untrusted inputs, the terminology from security. Modern secure coding guidance would generally tell us that if you're handling untrusted inputs, you should be very careful or just default to using an advanced tool like a fuzzer. And in most discussions of this problem area, we would probably just call every JPEG untrusted, regardless if we think we know where it came from, and just move on. But I think the idea of control is actually a little bit more illustrative. Let's look at add1 again. If I make my add1 function callable by random users on the internet as a web RPC, how much should I be worrying? Do I need to randomly generate 1 billion inputs for add1 before I'm comfortable exposing it to the internet? Or do I exhaustively iterate through all integers? Does anyone think that this is a good use of time or compute resources? On the other hand, if I make my decode JPEG callable on the internet, does anyone have concerns? Yes, we absolutely do. Which is to say, it's not just about trusted or untrusted inputs. I think it might not even be primarily about that. It's about how much intellectual control we have over the functionality in question, as well as the structure of the input itself. So popping up the stack a level, with the ideas of statistical and intellectual control in place, we could look at the question of what is enough testing and do a little bit better than I'll know it when I see it. I would argue that we can start building a little flowchart. If we have intellectual control over the software that is being tested and the structure of its inputs, then well-chosen unit tests, like proof by example, is actually pretty sufficient. In fact, had Knuth coded up the priority deck that he was writing about and run an even couple basic tests, I think most of us would take that as pretty solid evidence that the class actually works, both in theory and in practice. If we lack intellectual control over either the software or its inputs, then question mark, we're going to need something stronger. This is not entirely satisfying, but it's a start. It's an improvement over, I'll know it when I see it. If we go back to software design concepts, there are other ideas that we can leverage here. In particular, let's touch on design by contract. DBC is an idea that dates back to the late 80s and I think the beginning of the object-oriented programming movement. In a nutshell, DBC is about applying some formalism to the behavior of a bit of software. As with a lot of design ideas in the 80s and 90s, some proponents were maybe a little zealous about the approach, requiring that we had very formal specifications produced for every type and function and every piece of software. Personally, my suspicion is that the basic ideas and vocabulary of DBC are critical for effectively all software engineers, but we might need to be a little judicious in where and how we apply that formalism. Sometimes there are things that are obvious, and even when they aren't obvious, we might not need the formalism in the presentation. The essential point is that we've thought about it and documented sufficiently the behaviors of our interfaces. Personally, I write a lot, and I think of contracts in this terminology kind of like writing an outline for a paper or a talk. You're planning out what you're going to do before you sit down and do it. So let's return to add1 and look at the doc comment that I included there. In DBC terms, given is what we might call a precondition. This is a property of the input or the program state that must hold when this function is being called. And so long as that property is true, return or some other description of side effects or modification to program state are what we would use to describe the post condition. This is return value or program state guaranteed to be true after the function has completed. Now, in this case, I would argue that the preconditions here are incomplete. Our specification doesn't cover all the possible inputs, even for the types that are implied by this function. What happens if we are handed a string, but its value is not well-formed non-negative base 10 encoded integer? If in our tests, we assumed that throwing value error was the correct behavior for that, but strictly speaking, our contract is not telling us what to do there. Maybe we should throw value error. Maybe we should return none. Maybe we should just abort. So if we want to be good API designers, we should probably aim for total coverage, specify all of the behaviors of our function. For the types accepted by this API, should be exactly one precondition that covers each possible set of input values. And that might lead us to adding something to our doc comment contract. For instance, throw value error for any other input. Now we can see that add1 has two distinct behaviors, the nominal case as well as an error case. In order to be reasonably tested, we need, obviously, at least one unit test for each behavior. so we could update our testing guidance flowchart accordingly. For each behavior in the contract, do the previous. Now it's a loop. This feels a little bit better because it's not just about IC over the API, it's kind of behavior by behavior. Almost all of us can probably reason about the simplest error handling cases for decode JPEG, even if we can't mentally reason about the nominal case. Going back to look at add1 and our tests, now we see that we have a bug. As specified, -2 ought to throw value error, but currently it returns -1. We over-implemented. And this highlights one of my favorite points of bringing in DBC as ideas as part of your development process. Even in these relatively simple scenarios, there needs to be a three-way consensus. All three of the implementation, the contract, and the tests need to agree. If any of them don't, then there's a bug somewhere. Maybe you specified the wrong thing. Maybe it's that your contract is not saying what you wanted it to. Maybe you implemented the wrong thing, or maybe you got the tests wrong, right? In this particular case, I think we have two options. We can either fix the implementation, which would make it a little harder to implement and slower, or we tidy up the contract itself. So let's try that. When trying to specify the contract for add1 in handling of negatives, we could do one of two things. We could define the behavior to match what positive numbers do, which is very easy for this implementation, or we can do a thing that original DBC purists might hate, but in practice is fairly common in computing, which is we leave it undefined. If the rules of DBC are effectively, for a given invocation of this function, if exactly one set of preconditions captures the input, the associated postcondition must hold after the function executes. If there is no precondition that describes this invocation, there is no associated postcondition. Any behavior is allowable. There are two important things, two critical things to realize about this. Software systems with partial contracts and undefined behaviors are far, far, far harder to use well or safely. I know an awful lot of C++, and it is riddled with undefined behavior. The C++ community just refers to it by shorthand as UB because it is such a common term. By comparison, a higher level language like Python has vastly less UB. You really, really have to try to get it into a state where there isn't a definition of correct behavior. Implementations of systems that leave UB in place can, however, be more efficient. Let's consider a minor variation on add1, but now I'm going to do it in C++. And weirdly, I'm not changing languages here because of easier access to UB. I'm changing languages here because I need strings to be mutable if we want to do carry the one in place, and Python string immutability ruins the example. Here, I'm making the problem a bit more complex. It is still arguably the simplest and earliest algorithm that any of us ever learned, carry the one. But because we're allowing for inputs up to 10 to the 10,000th, substantially larger than the number of particles in the universe, the simple answer of converting to int or 64-bit int doesn't remotely work. And further, by doing the work in place, we can avoid doing order n work in most cases. Only in the case of a string of all nines do we even have to look at all of the data. The average case, assuming uniformly distributed inputs, is order 1. Here we can see the complete versus partial contract issue more clearly. If I added to the contract for invalid inputs, throw an exception or return an error, we have to look at the full input, potentially all n digits. If we leave the contract only partially specified, our average case drops from order n to order 1, and there are going to be times where this matters. We see echoes of this trade-off all the time, from high-level API design to programming languages. Tons of stuff in C++ is UB, specifically because it's too expensive, either at compile time or runtime or both, to diagnose and prevent those behaviors. Use after free memory safety bugs? This is UB because retrofitting memory safety into C and C++ would invalidate tons of old code and potentially add runtime overhead that we can't afford. Type punning is UB in C++, because once you have an object model and object lifetimes, you really do have to run the constructors and destructors if you want to ensure correct behavior. ODR violations are UB because compile and link time operations don't have enough information or compute time to prove that you didn't violate the one definition rule. You can only specify each entity one time. C++ fundamentally defines well-specified code, but leaves lots of pits full of spikes just on the edge of that specification. And the most surprising side effect of this, since there is UB that is detected at compile time, this also means that there are inputs to a C++ compiler that would generate a binary but aren't formally a program. Their behavior cannot be defined by the language standard. There are false positives in C++'s notion of, is this a program? And this is entirely due to specification versus efficiency trade-off, contracts and partial specification. In theory, UB can do anything if there is no post condition to satisfy, so any behavior at all is allowable. There was a page which I did not write at Google that described it as, if you have UB in your program, it is allowable for your program to email Titus and say that you are a bad programmer. That is technically true and theoretically possible, but in practice, the most likely result that you're going to get is a crash. Hopefully that's an immediate crash, but again, anything is possible. So what do we do when we have a really complex API beyond our level of intellectual control, but we want to at least achieve a reasonable amount of statistical control, especially while we have to worry about UB in our choice of programming language? First off, since it's undefined, we can implement it to do whatever we want. There is no valid program that relies on that behavior, and this turns out to be pretty handy. Advanced tools in dynamic analysis, especially things like the sanitizers in Clang, rely on exactly this. You can modify the compiler to notice when you're doing undefined operations, say accessing memory that isn't currently valid, and cause the compiler to emit code that does whatever you want, especially including aborting the program and logging a bunch of diagnostic information so that you can track down exactly what just happened. If you do this effectively and you tie it into the compiler in the right ways, overhead on such things tends to range from 10% to maybe 2 to 3x. So you're probably not going to deploy software with that instrumentation to users at scale, but you could probably at least run some pretty big tests with it. So let's look at our work in progress for how to test this API. Right? If we lack intellectual control over the software, its inputs, we need something stronger. If we lack intellectual control on the software itself, on decode JPEG, dynamic analysis might work. If we lack intellectual control on the input, selecting a couple easy test cases doesn't really tickle the real bugs. And dynamic analysis by itself doesn't prove a lack of UB or other bugs. It argues a lack of UB or bugs in the code that was actually executed with the inputs provided. If we don't have powerful ways to generate inputs, we don't get statistical control on those hard cases like decoding a JPEG. This is where fuzzers come in. I said I'd get there. Fuzzing also dates back to the late 80s and started as roughly randomly generate inputs and just hammer this thing and see if it crashes. Remember, crashing is a common subset of the possible behavior of triggering UB in your programming language of choice. Modern fuzzers refine this with ideas from symbolic execution, dynamic analysis, program analysis, and all sorts of other fields in order to aggressively find new paths through the program under test. In particular, I really like coverage-guided fuzzing with dynamic analysis. By working with the compiler and the operating system, we can monitor which paths have been executed out of each branch. That's if statements and other control flow. And with a little bit of logic, we can generate inputs that trigger many, many distinct code paths. Coverage-guided fuzzing combined with dynamic analysis tools like sanitizers is an incredibly potent recipe for getting a lot of statistical control over a complicated API like decode JPEG. One of my favorite demos ever is this one. This is one of my former colleagues, Kostya, doing a live demo of coverage-guided fuzzing with address sanitizer, trying to find 2014's Heartbleed bug. For those of you that weren't around or weren't paying attention, Heartbleed was a very severe issue in OpenSSL. Sending some bad inputs to an SSL endpoint could allow you to read the private keys and totally obviate all of the encryption that involved that endpoint. This caused widespread industry panic as the majority of the software on the internet had to be patched and updated ASAP. In this 2015 talk, Kostya shows this type of fuzzing hooked up to the OpenSSL packet processing interface, and it finds the heartbeat bug in about 10 seconds on a 2015 era laptop with no pre-chosen inputs. This is certainly not proof of correctness, but fuzzing provides a powerful amount of statistical control. or at least in some cases. It's a powerful amount of statistical control against crashes and other forms of UB in the language, but fuzzers for higher level languages like Python or Java might trigger full crashes of the interpreter or the JVM in a few places, but probably not. And in many cases, we're just left with, was there an uncaught exception? And it's one thing to have machinery that handles, did we do something undefined or trigger something unhandled? But it's a much different thing to ask, is my program working as intended, right? And for that, we might need to evolve fuzzing Pokemon style into a more advanced form. I would call this property-based testing. Property-based testing is to specified contracts what fuzzing is to undefined behavior. This is maybe not a perfect analogy, but it gets us a lot of the way there. Property testing takes ideas from fuzzing, generation of random inputs, and says, maybe we should look at the result of that computation, not just the side effects. So here's an example from the Google Fuzz test system, which ties in very nicely with Google test. This example says effectively, run coverage guided fuzzing on the input I. Rather than sending in totally random values, we're going to match the contract of my API, which is defined to return true if we handed a positive input. So the domain here that we're fuzzing over is limited to positive integers. For every such input, the call to my API should return true. Additionally, since this is running in the same infrastructure as sanitizer instrumented coverage-based fuzzing, if any inputs happen to trigger the types of UB that we're afraid of, we get good diagnostics on those failures as well. So what can we say about the behavior of my API on inputs that aren't positive? That would depend entirely on the contract, at least as far as any logical assertions go. But one thing that we could do is just add a second fuzz test that has no assertions. Since this is still coverage guided fuzzer under the hood and we're still using sanitizers, we could at least check for language level UB. This is not testing any properties of the code at this point, but at least ensures that we're not calling this out of contract doesn't make things any worse. And that gets to a broader point about property-based testing. It's not quite as easy to apply as fuzzing. You need to be able to express some property of the output based on a completely random input. In cases like return true for all positive integers, we know kind of what to do. But for something like decode a JPEG, if I feed you a random JPEG, even if I promise it's a valid one, what sorts of assertions can you make about the resulting image after it's been decoded? We know it's an image, but if we let the random generation specify dimensions and colors and content, how do you assert anything useful about the results of decoding it? In the degenerate case, property-based testing might require you to re-implement the API that's being tested in order to validate that a randomly selected input does what you expected. And that would be a lot of work, and I don't see that we're actually going to do that. But there are cases, and they're not rare, where you can do a lot better. There's a blog post by a man, Scott Woloshin, that has a very nice write-up on the types of properties you might be able to exploit with this approach, depending on the APIs in question and their contracts. Sometimes if you have commutative operations, try asking your property-based testing framework for multiple inputs and apply them in different orders. That is, if my API on A comma B is supposed to be the same as my API on B comma A, make sure that that's true. Sometimes if you're implementing an operation and its inverse, test that a random input will round trip. This works for encode, decode, encrypt, decrypt, serialize, deserialize, etc. Sometimes things are invariant, right? Given an input or operation on existing state, find those invariant properties. If you filter a collection of objects, the resulting collection will certainly not be larger. If you apply a map transformation to a collection, the resulting collection should be the same size. If you modify a single element of a collection, the others should not change. If you modify one property of class person, the other properties should not be changed. You get the idea. On data structures, this also works for things like arity and sort order. If you insert n distinct elements into a set, you should get those same elements back out. If the set happens to also sort things, you should be able to iterate through them in sorted order as well. Sometimes if your operation is idempotent, that's worth testing as well. If applying the operation more than once is guaranteed to yield the same result as doing it one time, this is an easy and valuable property to test. Once in a while, it's hard to prove but easy to verify. If you're implementing a complicated algorithm, there may still be an easy answer. Prime factorization is a clear example here. Doing the factorization is hard, but checking the answer is pretty easy. You could also imagine using this approach to test a randomly generated maze is actually solvable. I certainly don't remember the algorithm for generating a good maze, but running breadth first search on an existing one is pretty reasonable, and I could write breadth first search in my sleep. Or sometimes you do have a test oracle. If you happen to have two versions of an algorithm, that's the very easy case. And while it seems wasteful in the general case, it does come up sometimes. Maybe you're doing a rewrite for efficiency, or maybe you're doing a clean room implementation of a component, or maybe you're swapping out lower level infrastructure and need to ensure that a higher level behavior hasn't changed. Now, it's certainly not the case that every API that we could be implementing is suitable to any of these properties, but I will assert that in well-structured projects, you're going to find a larger density of utility functions and classes that can be validated this way, because time and time again, we find that testability is strongly correlated with good design. If you can't test it, you probably didn't design it with the right abstraction boundaries in mind. So with proper understanding here of dynamic analysis, fuzzing, and property-based testing, we can fill in our flowchart a little bit more. For each behavior in the contract, if we have good intellectual control, unit tests suffice. If we lack intellectual control, we need fuzzing or property-based testing, primarily dependent on what the contract said and whether there are clear properties that can be tested. So when it comes to testing or what is computed, this little flowchart covers an absolutely huge swath of the problem space in my experience. But this is still not quite the whole story, because sometimes it's not just a matter of getting the right answer, it's also a matter of how we got there. And that brings us to one last intersection between design and testing, and one last piece of borrowed vocabulary. In the design literature, getting the right answer is due to getting the correct functional attributes. This is basic computational correctness. But sometimes we care about other things as well: security, latency, scalability, readability, reliability. The shorthand is often the ilities, and there are two common terms for the counterpart of our functional attributes. There's non-functional attributes or quality attributes. I vastly prefer quality attributes because non-functional sounds a lot like broken. So it's one thing to say, here's JPEG, decode JPEG, it decodes a JPEG. But it's another thing to say, here's decode JPEG. On nominal inputs, it's expected to return in under 100 milliseconds. It consumes a bounded amount of memory, and it will not crash even on malicious inputs. That is a harder thing to prove. For the sake of discussion, I'll focus on latency as our exemplar quality attribute. If we want to test whether decoding actually returns in under 100 milliseconds, how do we test that? I think we certainly have intellectual control over the matter. We know how to measure the passage of time. We know what 100 milliseconds is. We hopefully even know what a normal input is. So we run one test on a representative input and time how long it takes. I don't think any of us would be really convinced by that approach. I know I wouldn't be. If we want to get a sense of how long something takes to compute, we probably need to run it a few times. And even then, there's going to be some big question marks on the result. I'm sure you don't need me to say it out loud, but computers are remarkably complicated devices. Cache effects, NUMA nodes, processor scaling behaviors, virtualization, optimizing compilers. All of these can and do have substantial effects on processing speeds, and thus latency and benchmarking results. The best we can really say for testing of quality attributes like latency is that it tends to require an empirical approach, experimentation. And the more that the system under test matches the behavior in production, the more that we can actually have faith in those results. So we need representative hardware, build configurations, inputs, load on the machine, all of those things. There's a host of other issues to pick apart when we really get into the difference in handling quality attributes versus functional attributes. It's far more than we have time for in this talk. But I will summarize with one more George Fairbank's quote on the matter. Functionality is localized. Quality is diffuse. That is, we can ask where the login code is. We can't ask where the security code is. It's a matter of everything not being insecure. We can ask where the JPEG decoder is. We can't ask where the performance code is. It's a matter of not letting anything be slow and wasteful. This is one of my favorite insights of the past year or so. Even if we have a good sense of how to write good code and how to test it, If we really want to achieve any given quality attribute, say good performance, good resource usage, we have to be diligent everywhere. And that is hard, so you need to pick your desired qualities wisely and carefully, because having more than a couple of them is really hard and expensive. And that leads me to one last tangent. In the last few years, I have spent a lot of time thinking and writing and speaking about the software workflow, the software process. So much of the software workflow is fundamentally about catching functional attributes, functional defect reduction, bugs. We write unit tests, we configure our CI systems to manage primarily functional correctness. We get some very generous timeouts on those CI systems, but that's mostly just to catch cases where a test is deadlocked. Most of the time, our CI systems and test frameworks aren't actually monitoring for minor regressions in performance. And that reinforces the idea that we need to rely on not just run it once to get functional evidence, but we need to run it a bunch of times and rely on empiricism. It's a matter of tracking state and differences in moving averages over time, rather than overly anchoring on a single bogus sample. If most of our workflow, CI, et cetera, is about catching regressions in functionality rather than quality, what parts of the workflow are actually about quality? Once in a while, we can build tools for a few qualities that we care about and can figure out how to get at programmatically. This is stuff like benchmarks and auto formatters, maybe. But in the end, the primary human activity in the workflow is pair programming or code review. It's only in those cases where another human is looking at our code and we really have someone to answer to on quality issues. The questions of, hey, is this sufficiently documented? Is that computation wasteful? Is this implementation overly clever? These are human matters. These are quality matters. And that itself gets to the heart of a lot of issues that we might have in code review. Sometimes it feels nitpicky or unimportant. Sometimes you're not sure what you need to be focusing on or how hard to push back. But it's a slippery slope, because if we don't have any other safeties in place to maintain our approach to quality for whatever quality attributes we are investing in, we're going to have a bad time. And this quality attribute discussion leaves us with one additional modification to the testing flowchart. For each behavior or requirement in the contract, if it's a quality attribute, we need to take some sort of empirical approach, figure out a way to run experiments, and many samples are likely going to be needed. And otherwise, everything from before stands. Before working with George and having these bits of design vocabulary to draw from, questions like what is enough testing or how do I test this API were really annoyingly squishy. I could give a couple examples, but never anything that felt even remotely objective. With ideas of intellectual control, design by contract, and quality or functional attributes, it becomes much easier to discuss the APIs and problem complexity, making it far more straightforward, although not entirely objective or mechanical, for us to judge what is an appropriate level of testing. Modern testing practices like property-based testing and coverage-guided fuzzing are incredibly powerful, but without these design ideas, it's hard to know exactly where to spend that effort, where the cost is going to be worth it. Discussions and problem-solving exercises like this have really highlighted for me the deep connections between software design and software testing. As I said at the beginning of the talk, it's really easy to dismiss design as being abstract and impractical and theoretical. But when we see it as a vehicle for explaining practical concerns like testing, the utility becomes far more obvious. And the reverse, I think, is also true. Testing is terribly powerful. Continuous integration systems, unit test practices, and the like are responsible for keeping massive old projects not only functional, but malleable enough to change and evolve over time. But it's one thing to have tests, and it's a far different thing to test well. The past few years have convinced me of one thing above all. It's hard to understand what is good testing without drawing on critical ideas, vocabulary, and lessons from software design. So I, for one, think that these are really two sides of the same thing, the calculus and physics of day-to-day software engineering. Thank you.
Thank you, Titus. So let's move on to the questions and answers. The first question is, people say they're using generative AI to do their programming. Can we test the AI output adequately? And what if testing too is overtaken by AI?
I think that, so I have a lot of thoughts on this. First off, for anyone that hasn't read it, there was a great article in Communications of ACM a couple months ago on what is the productivity boost from things like GitHub Copilot. I love that article. Some of the researchers there were involved in Copilot, and I think they did a great job of kind of summarizing the trade-offs and all of that. When it comes to generative AI and generating your code and or generating your tests, hey, if you've heard me talk in other contexts, you've probably heard me say Hiram's Law. If you get into this space of Hiram's Law is you can't tell the difference between what's promised in the contract versus what's accidentally implemented. And if you're having your generative AI look at your code and generate tests from that, that's just going to make Hiram's Law 10,000 times worse, right? There's no way from the code to tell whether a given behavior was intended or accidental, right? And so I'm really nervous about anything that's like, we can let you stop writing tests and we'll just synthesize all of your tests for you. Like, this is a surefire way to just make sure that nothing can ever change again and your test quality is going to go down. I think for generating the code itself, there's mixed signals so far. I don't think we've had a whole lot of luck with like, this is really accurate in the large scale. I think it's more practically, a 10 or 20% productivity boon for moderately experienced engineers as a fancy autocomplete. And that's still not nothing, that's pretty good. The model that I would really love to see us move to, and I kind of assume if generative AI in this space is ever going to be all that valuable, every other generative AI interface at all is a prompt, right? And you specify what it is you're looking for, and then it tries to do that. And usually it doesn't do exactly that, but it gets close. I would argue that the workflow should be, you type into a prompt the contract of what you're trying to implement. It synthesizes some tests and says, hey, does this look like the behavior you actually care about? And you go back and forth a couple times. And at the point where you're like, yeah, this looks pretty good, then it can generate the code. And if it generates the code that actually passes the tests, this is fine, right? This, I think, just highlights, yeah, design by contract is probably becoming more important, not less. But anything other than that, I think there's only so much intent you can infer from the existing code or a prefix of the code. So the autocomplete thing is a little limited in my mind. Synthesizing tests from code is just a nightmare. Like, this is the only thing that I think is going to actually do all that much. And I still worry substantially that in most other forms, like when you look at generative AI, it's not exactly that precise. Like if you use AI image generators or text or whatever, like it gets the gist of it, but it's not precise. And so far, coding kind of needs to be pretty precise. So like, I don't think this is going to put us out of jobs anytime soon. Once we get to general intelligence AI, like, yeah, that's a different story, but we're not there yet. A couple more years.
Cool. Next question is, how do you feel about strong typing as a way to introduce implicit design by contract? And in addition to strong typing of data, is there a consensus on the protocol concept to demand certain capabilities?
Yes, typeful programming, strong types, like generally speaking, absolutely a fan. You can sometimes maybe in theory go a little bit too far with that. And there are some things that become a little tricky sometimes. But whenever possible, yes, if you can encode it in the type system, the type system is there for a reason. I think a very clear example of like, yeah, this is a pretty good idea. If we look at things that we, stringly typed APIs, is we chose not to use a proper type for this, and we're just passing everything around as a string, and boy, that goes poorly, right? Like the lesson that needed to be learned there is use a stronger type, use a better type, use something, yeah, strongly agreed. In terms of protocols and more advanced things, sometimes yes, I don't know. I don't think I'm not sure if that's a day-to-day programming space, but I'm open to it. We'll see.
Next question is, how do you see test first as compared to design by contract?
I think that those go hand in hand. I would much prefer to see write out the contract, then go write the tests, and then start implementing from there. I think that that's more likely to work. I would be perfectly okay with start writing some tests, infer the contract, so long as you're really rigorous about catching all of your edge cases in that. But I kind of feel like do the simplest, most flexible thing first, which is write down the contract and then start with tests and then do implementation. And part of that is just pre-writing, like the reference I made to write an abstract, have a plan. Having a plan helps. But the other part of it is, I think, especially as it becomes increasingly obvious that, yes, you're going to write tests. This is an industry practice for a reason. It is a heck of a lot easier to tackle the intellectual challenge of, let me think about which cases here are going to be hard. Let me think about which behaviors in my contract are hard to get right. And then you sit down and you write out the tests for those. And then you feel good when you start implementing things and your tests go from failing to passing. Whereas if you do the thing that a lot of us started out doing when we were younger, you sit down, you write all of the code, and then you're like, yay, my code is great. I'm so good at this. Hooray. And then it feels kind of wrong and gross to sit down and try to prove that you did a bad job by let me find all of the hard cases, right? Like fear and pride and, all of these very human emotions kind of get in the way of us doing a better job of that. And so write the contract or the tests first, probably, hopefully the contract. Don't write the code first. It's not psychologically a great plan.
Next question is it a best practice for SDK API providers to make available test implementations for all features before releasing version 1.0? And any good examples to highlight that are developer friendly?
I think I would buy that. I don't think I can say that with great confidence because I haven't been in a space that had to do that. But conceptually, I really like that idea. And I think even beyond providing test implementations for your SDK, providing test facilities for whatever API you're producing, that is so critical. It kind of blows my mind and drives me a little nuts when companies are putting out production web APIs to call, and there's absolutely no way for you to write your code against that API and test it without calling that API for real. That just doesn't feel like good user experience or good handling for API providers. I think we have to accept that making your APIs testable is part of best practice for providing an API to anyone. And so if you're SDK, you usually feel like conceptually SDK is a little bit smaller and easier to just run it live. But if your SDK has complicated expenses or billing or side effects or things like that, if you have a credit card processing SDK, have a test, have a mode in there for testing, have a mechanism to test that.
Next question is, for teams that use semi-custom firmware and host-based scripts to qualify and characterize successive generations and variations of hardware, how do we balance the quality of the reusable code base and the expediency of the ephemeral or even single-use code? There may be zero budget for infrastructure. There may be a fixed time limit on either solving a problem or leaving it unsolved and moving on.
Well, I would argue if there's zero time budget for infrastructure, you've got a problem. I've seen some pretty compelling like in-depth research studies that are over and over coming to the conclusion that if less than 10% of your like organization's budget is spent on, if less than 10% is spent on infrastructure, you're probably not actually being very successful. It's gonna be a little random at that point. But as to like, yeah, when you're down at the level of like individual micro architecture releases and, you know, like here's this week's hardware, yeah, stuff gets hard. Ideally, you have consistent APIs and specifications for those things, but I've worked with hardware vendors and, you know, there are bugs in those things. You may wind up having to try to build an abstraction layer over that to just say like, no, this feature is broken on this release, or let me try to hack around the bugs in this release. Especially if you're going to try to support multiple, you know, architectures or microarchitectures live for users. You'll have to paper over those differences at some point. But yeah, when you're down at that level, it gets really hard. When there is a contract and your underlying layers are violating it, yeah, that's tough. I don't have a better answer to that.
The next question is related to mutation testing. So what about mutation testing as an option for tackling UB? What are your thoughts on the practicalities of mutation testing nowadays?
I love mutation testing, but for different reasons. So mutation testing, for everyone out there, mutation testing is the idea of, okay, can we classify the most common sort of basic programmer errors? So this is stuff like adding a not to a conditional statement, or swapping X and Y for Y comma X, you know, getting rows and columns inverted, doing your lookups on matrices transposed, all sorts of, you know, basic common sort of things. And the idea being, if you build up a pool of those common bugs, we'll call those the mutators. If you take the code that you were trying to test and you apply all of those mutators, you get a bunch of mutant versions of your code. And if your unit tests don't catch those bugs, then your unit tests probably aren't quite robust enough, because there were, you know, nearby things that are clearly a bug that you didn't catch. And so the sort of common mechanism for looking at mutation testing is trying to evaluate, like, do I think that there is sufficient test coverage by virtue of, are all of the mutants squashed by at least one of my unit tests? And the normal algorithm is run unit tests for each mutant until some test fails and then move on to the next mutant. What I like conceptually, like that's great for evaluating, like, yes, you have a gap in your testing. What I like conceptually even more is don't bail early and build up the full matrix of all of the mutants and all of the tests. And if there are any rows or columns, I'd have to think about it. If there are any chunks in that matrix that are complete duplicates of each other, right? If two tests catch exactly the same set of things, then those tests arguably aren't testing distinct properties, right? They're entirely overlapping. So run whichever one of those is faster and maybe disable or defer the other one. If you have one or two tests that catch all or almost all of the possible mutants, those are your highest priority tests, right? And so you can start to get into like test selection, filtering, and prioritization by virtue of looking at it in this sort of mutation testing inspired, like which is giving me the highest signal, which is giving me the broadest spread, like it's a minimum spanning set of unit tests to catch all of the mutants. So I think mutation testing has lots of really interesting properties, especially as we start getting into larger projects, more tests. CI is expensive. Maybe we don't need to run every test on every change. How do we start prioritizing these things? So there's very cool stuff in there.
Okay, I am afraid that we have run out of time today. I'd like to thank Titus again for his informative presentation and insightful answers to the many questions. I also want to give a special thanks to each of you for taking the time to attend and participate today. This talk was recorded and will be available online in a few days at learning.acm.org. You can find announcements on upcoming talks and other ACM activities at learning.acm.org and acm.org. Also, please fill out our quick survey where you can suggest future topics or speakers, which you should see on your screen in a moment. On behalf of ACM, Titus Winters, and myself, David Sankel, thanks again for joining us, and I hope you will join us again in the future. This concludes the talk.
Thanks, everyone.